All right, so I didn't record all of 2.3 stuff, but we're on 2.4, measuring the spread of data. So I'm going to give you a data set, same data set that we had earlier. If I can remember what the data set was. I think it started with a 4, 6. Maybe it was 4, 5.
3, 4, 7, 10, and 16.
Thank you. I knew I was close. All right. So that's what we started with. We started with these numbers. And those numbers have a mean. Those numbers have a standard deviation. And the standard deviation measures how spread out the numbers are. Okay. So the mean again is 7. Mean just measures the center. Mean is 7. But I want to know how spread out the numbers are. The bigger the standard deviation is, the bigger the spread. It's the measurement of the spread of numbers. And there's again applications for standard deviation that we'll use, which is really important. Standard deviation, probably one of the most important topics in statistics overall. Just understanding what it means. But we're going to measure how spread out those numbers are. So if I find the standard deviation, I'm going to do it on my calculator. So again, I'm going to go back to list. I'm going to save the data that's in list 1. Let's go to list 2 this time. So go stat. We're going to go here again and press enter. And we're going to go to list 2 this time. So let's go to list 2. In list 2, let's enter those values. So 3, 4, 7, 10, 16. And we're going to this is a revisit where we just did. Our data is in list 2. Now we're going to find the mean and the standard deviation. We're going to find the sample standard deviation. There's 2 standard deviations. So we have population standard deviation. Which is this symbol, sigma. And we have sample standard deviation. Which is S. I don't even need that word. S. S is sample standard deviation. Did everybody get those entered into a list? Okay. I want to know what the mean of that list is. Well, it's 7. How do we find the mean of the list? We're going to go to stat, find the standard deviation, stat, calc. We just went here. Again, we're going to revisit this again. Go to calculate. Go to one variable stats and press enter. Again, you might need to quit if you get out of the screen. So go to one variable stats. But now we're going to enter second 2. We want the data that's in list 2. So second 2. That'll give me the statistics for this data set. And again, we already did this, right? We had the mean was 7. Or I'm sorry, the mean was 8. The median was 7. But there were some other numbers on there. We had S and sigma. Okay. So population standard deviation, that's the sigma. What is that number? Anybody get that number?
4.69.
4.69. Okay. I was around 7. S, that's standard deviation.
5.2.
5.2. That's how spread out those numbers are. Okay. Spread of the data. Does everybody agree with those numbers? Anybody confused about where we're at right now? Okay. Don't worry about it. So this stack. No, just that. That's what it is. Your data set is 2, so that's 7. 5.2 is 4.7. We're all there? Okay. This is a population standard deviation, which is calculated using a nifty formula. This is calculated using a formula as well. So one sample standard deviation, one's considered population standard deviation. There's another measurement of spread, it's called variance. There's variation in data sets, and variance is a measure of that, but variance is not really important. We use variance to get standard deviation. It's just a formula thing, okay? But I'll get to that in a little bit. I'm just gonna pop in here with a new data set. If this data set has a sample standard deviation of 5.2 or about 5, that's how spread out those numbers are. They're spread out by 5. And it's hard to see in the data set. The numbers go from 3 to 16. They spread out by 5. What if I have another data set? 3, 5, 7, 10, 21, 37. Okay, so we don't need to enter these numbers. You don't need to write these numbers down. I'm just using this as an example data set. If this data set has a spread of 5, that measures how spread out the numbers are. Do you think this standard deviation is going to be bigger than 5 or smaller than 5? Think about how spread out these numbers are. Is there more spread for this data set or less? More. Okay. This data set's spread out a lot more. So the standard deviation is going to be bigger for this data set. Does that make sense? So we're going to calculate standard deviation would probably be a bigger number, probably like 10 or 12 would be the standard deviation for this data set. Does that make sense? That standard deviation is about 10. How about this data set? Standard deviation. Can we think about what a standard deviation might be? Probably in the hundreds or something like that, right? Because we're talking hundreds now. Standard deviation is going to be in the hundreds. Standard deviation is ultimately used to find a percentile. Okay, when you take a state test or a college entrance test or the GRE or the PSAT or any of these high stakes tests, they give you a percentile. And they say, oh, you're in the 90th percentile. If you're in the 0th percentile, that means you scored the lowest. If you're 90th percentile, that means you scored pretty high compared to the average. So what we do is we take one value and compare it to the average score. And that is a percentile. And how is it used? It's used by finding the standard deviation of your data. So again, nurses' salaries, they average about $60,000 a year with a standard deviation of $15,000. So if the mean, I'm going to use a population value for here locally, $60,000. The standard deviation for all nurses is about, I think I said 15, but it's probably more like $10,000. Okay, so we could think about if you're a nurse nursing salaries. Okay, 60,000 is in the middle. That's the average. Some nurses make more, some make less, but most make around $60,000. So we use $10,000 to compare where you're at. Okay, that's nursing salary. If you're an engineer, you work for Lockheed Martin, the average salary is about 90,000. Standard deviation, there's more spread in engineering, about 20,000. So engineers, there's a lot more spread in engineering, right? Some engineers make a whole lot more money, but you know what, some make less. There's more spread. Standard deviation, the simple basic definition of standard deviation is measurement of the spread. Okay. I'm going to get into doing this by hand because that's what the book directs us to do. That's what the course is set up to do. But I'm not going to do a test you on it. Okay, I used to test on it, but now things have changed in the state of California with community college. We can do it on our calculator. So I'm going to show you how to do it by hand. You may get a little bit confused, but it's just a good thing to know. Okay. And then we'll do it all on the calculator. All the standard deviations we'll get on our calculator, but I'll go back to that in a little bit. But that's just a basic idea of how standard deviation works. So going back to our original data set there, I'm going to give you the formula for variance for population standard deviation. I'm going to give you the formula for sample standard deviation. There's 4 formulas that you're going to see. These are all in the textbook. And they're going to get a little crazy, but bear with me. I'll explain exactly where they come from, but this is the most pure mathematical thing that we're going to do. So this is called variance. That symbol should look familiar. Some, that means we're going to add a bunch of things together. And if you're following along, this is in the textbook too, by the way. If you're on the ebook, the page number is a little bit different. Population variance is on page 83. Population variance, page 83. They use a capital N regardless. This, again, that symbol is called sigma. My students like to call it the O thingy. Call it the O thingy if you want to. It's a sigma, it's a Greek letter. Okay. This is a summation. That's the mu. That's the mean. I'm going to do that formula with this data right here, with these numbers. Okay. Just like finding the mean that we did earlier. We added them all up and divided by 5. I'm going to do this formula over here. This x is each of these. Remember x1, x2, x3, x4, x5. Okay. Each of those values are x values. There's one variable. We have another variable that would be called y, 2 variable statistics. We'll get that way later. But for right now, we're just going to take the first number and subtract the mean. You guys remember the mean of that data set? Remember the mean was 8. We found the mean already. The mean is 8. Now we do the formula. 3 minus 8 squared. The first number is 3 minus the mean, which is 8. Square it. Now we do the sum plus the next number. Plus the next number. Yeah, I'm gonna keep going. I'm just gonna do that. I'm gonna do the parentheses now. I'm gonna do the numbers in the parentheses. This is variance again. All right, I did the parentheses. Next step is to square the numbers. I'm just following the order of operations, just like in 6th grade. Add them up. Oh wait, I gotta square them before I add. Square comes first. Parentheses, exponents. Multiply, divide, add, subtract. Okay. When you square, this is really important. When you square negative numbers, it's gonna be positive. If you punch this in your calculator, -5 squared, you'll end up with a -25, but variance and standard deviation are always positive numbers. Okay, so -5 squared is 25. Let's add them up. Point 2. Okay. That's what I got. I think. Maybe I'm way off. Yeah? That work? I don't have a calculator.
You must be a math teacher.
Okay. That's called variance. That's called population variance. We just did that formula. Okay. In order to go from variance to standard deviation, it looks confusing, but population standard deviation is also on page 83. In order to get population standard deviation, we got to do the variance. And the formula goes like this. Square root the sum of x minus mu squared over n. Okay, the only difference between those two formulas is the square root part. See the square, we're not squaring anymore. So in order to solve this, we would square root. So the variance is 22. How do we go from variance to standard deviation? We square root. I think the square root of 22 is about 4.7 or 4.69. How do you square root 22 on your calculator? Press second. Make sure you're on your home page. Press second mode to quit. And you're going to go second and x squared. The square root sign should pop up, and then press 22. .69. Yeah, we did it by the calculator. Calculator is pretty fast, huh? Let's take some time, especially if you have 26 values and they're all in the hundreds, like on problem 38 that we did earlier. Find the standard deviation for that data set. I'd much rather do this. Stat calc, one variable stats, and get these numbers. Okay, so of course you can always do that, but this is just, we're just learning, we're just understanding what standard deviation is. Okay, that's population. Now we're going to go for this S value, right? Sample standard deviation. So sample, in order to get sample standard deviation, we have to do the sample variance. And the only difference between these two formulas is the n. This is on page 84. Instead of n, we're going to do n minus 1. And sometimes they'll put a, instead of mu, they'll put a X bar here. Let me make sure. Yeah. So we're gonna subtract 1. Instead of dividing by 5, we're gonna divide by 4. What are we gonna divide by? So this 110, remember we got, when we did all this math? We got 110. The numerator, the top, this is 110. That doesn't change. But instead of dividing by 5, we're gonna divide by 4. So S squared is 110 divided by 4. Whatever that is. You do 110 divided by 4. Sorry?
27.5.
27.5. Thank you. That's called the sample variance. Lastly, the most important formula that you're going to use in statistics is called sample standard deviation. Again, page 85. How we go from S squared to S? We square root. So it's just a square root of that. S equals square root of all that stuff. Sum X minus X bar squared over N minus 1. So all that means just square root now. So go S, square root of 27.5. The square root of 27.5 should be about 5.2. So again, press second. X squared. That and enter 27.5 and you should get 5.2. Yeah, and it works. Yay for math. All right. This just became a pure math class. Lots of formula stuff. We get all that stuff we can do on the calculator. Anytime you get a data set and you're asked for standard deviation, you can do it on the calculator. So they give you a whole bunch of data sets and it says find the range. Oh, I didn't talk about the range. That's the max minus the min. We did range when we talked about frequency distributions. Find the mean, variance, and standard deviation. Okay, the calculator doesn't give us variance. The calculator only gives us standard deviation. So if they gave us 5.2, how do we get the variance? We square that number. To go to 5.2, 27.5, I'm going to square 5.2. 5.2 squared is 27.5. 4.7 squared is 22. So we go back and forth between variance and standard deviation pretty smoothly, because that's what the questions asked for in the homework. Find the population variance, population standard deviation. Find the sample variance, sample standard deviation. Find the mean of the data set. Okay. That's about half of what we have to do. Okay. Today. That's only half the stuff. That's doing the calculation stuff. Again, we could do all of this on the calculator, which is cool. So let's do it real quick. We have a data set already. This was problem 38 from 2.1. Press stat. Enter. And list 1 should have that big, huge data set with all those triglyceride numbers that was on problem 38, correct? Okay, so we're going to quit that screen. Let's go second mode. We're back to our home screen. We're going to press stat. Calculate. I guess I should put it up there. One variable stats. And we're gonna enter this one. Our X list is list one. Frequency list, we don't put anything right now in the frequency list. Leave that blank and then calculate. We get the mean for triglycerides. We get the population standard deviation for triglycerides. We get the sample standard deviation for triglycerides, problem 38. Those are big, huge numbers, aren't they? They're in the hundreds. Because we're measuring milligrams per centimeter cubed of amount of measurements of your blood, something that you would do in the medical field. So that's what I would expect you to be able to do, press these buttons. Okay, and that's the third time that we've done it today. Sound good? That's pretty cool. So you got 26 values. Oh, calculate standard deviation. Are you gonna do it by hand? No. Although I did have a student years ago that passed this class with an A. He never used a calculator. I thought he was a genius. He did it all. He found every standard deviation by hand. He had a big old page full of standard deviations every time we did a test or a quiz or anything. It was pretty crazy. It's like, I can't afford a calculator, so you do it by hand. Okay, I'm not gonna expect you to do that. Okay, do that formula by hand. Okay, you don't have to. All right. All right, so now I'm gonna apply the standard deviation. What is the application of standard deviation? What does it mean to have this as an application? Okay. Most populations are approximately normally distributed. So when I say symmetry, data is symmetric most of the time. Follows the bell curve. Like, you have instructors, any instructors grade on a curve? Have you ever had people grade you on a curve? A lot of people make up their own curve, but they're actually going to use the bell curve. Okay, it's called a normal distribution. Most data is normally distributed, but you know what? Grades and test scores usually are not normally distributed. They're usually skewed to the left. So the bell curve, there's actually a picture of a curve on page 88. They call it the bell curve. I like to use the word normal distribution. Because that's the actual statistical name of it, and that's what I'll use for most of the semester. So this bell curve just tells us that 34% and 34% is 68%. 68% of data is one deviation away from the mean. 95% of data is two deviations, and then 99.7% of data is three deviations away from the mean. All right, so let's talk about speed on the freeway. So the speed limit is 65, so everyone drives 65 or less, right? That's the case. Okay, not really. The average speed is probably about 65, and it might even be more than that. But if you consider, diesel trucks do have to drive 55 miles per hour, right? So there are vehicles going below 55 miles per hour. There are vehicles going above 65 miles per hour. But what's the distribution? Most of the cars are in between a certain range, okay? A range of values. So if I give you the speed on the freeway, if the average speed on the freeway is 68 miles per hour with a standard deviation of 5 miles per hour, I'm going to apply standard deviation using the empirical rule. And I'm going to draw a curve, okay? But before I do that, I'm going to do some calculations. I'm going to add 5 to 68, and I'm going to subtract 5 from 68. Is that really difficult math? I hope not. Add and subtract 5. Okay, that's the math I'm doing. Then I'm going to add and subtract 5 once again. So that's the math that I'm doing. Okay, so hopefully it's not too complicated. I'm going to make an x-axis. I'm going to put 68 right in the middle. And this curve, this is a bell-shaped curve. Draw as best you can. I've been doing this for many years, so I'm actually pretty good at it. But 68 is in the middle, 68 miles, this is its speed, miles per hour. Right at the first inflection point where the graph turns down and turns back up, right over here. And over here is about 1 deviation away from the mean. So again, I'm going to add that 5. And I will subtract 5. That's 68%. That's more than half of the vehicles on the freeway are going between 63 and 73 miles per hour on any given day, any traffic, anywhere, right? Sometimes there's more traffic, sometimes there's less. Sometimes you drive slower. Like if you're driving from San Luis Obispo to Santa Maria. Anybody ever do that? Someone did it today. Takes about an hour to get here from San Luis Obispo. It usually takes 35 minutes. 2 deviations. I'm going to add 5 more. 78. 68. Or 58. That's 2 deviations away from the mean. So I just added 5 more miles per hour. Okay, this is considered normal. So the mean plus or minus 1 standard deviation is 63 to 73. The mean plus or minus 2 standard deviations is 58 to 78. This is 68% of data. This is 95% of data. So 95% of cars are driving between 58 and 78 miles per hour. Have you ever seen a car go above? Have you ever been in a car above 78 miles per hour on the freeway? Okay, everyone's nodding their head yes. Have you ever been in a car below 58 miles per hour on the freeway? Some of you have done it today. Driving 20 miles an hour between San Luis Obispo and Santa Maria. Okay, traffic. It's called traffic jam. So that happens all the time, right? When there's a lot of cars, you have to slow down because there's too many cars. You can't drive 78 miles per hour, right? 95% of cars are going to be in between these 2 speeds, about. Okay, it's just an estimate, it's an approximation. Okay. 99.7% of cars, that's almost all of them, are 3 deviations away from the mean. So 1 more deviation, we subtract 5 again, 53. That's your diesel trucks, right? All the way up to 83 miles per hour. Very few cars are going above 83. On the one passed me last night driving. I live 2 miles south. Car passed me going about 90 miles per hour. As I merged onto the freeway. They had to go really fast. And they got off the freeway where I got off too. That was interesting. Good job. Especially with gas. When gas costs a lot of money, you know, if you drive an average speed, you'll save money in gas. It only makes mathematical sense, but a lot of people don't do it. All right. Anyways, that's using the empirical rule, which again is on page 88. And the empirical rule is used to calculate normal distributions. I can also calculate what's called a z-score, but z-score is used for calculating a percentile, which we'll get to a lot in chapter 5. So I'm going to hold off on z-score. I'm going to do another example of this using the empirical rule of mean and applying mean and standard deviation, because you want to compare 2 groups that are similar, right? We don't want to compare groups that are different. Okay, so this is speed on the freeway. I wouldn't use this distribution if you're driving down Broadway, right? It would be different speeds. So if I have male height, the average height of a male is about 5'9" with standard deviation of 3. female height, the average height is 56 inches with standard deviation of 2.5 inches. I hear females say all the time that they're short, right? A lot of females are short. Well, you're short compared to males. If the average height of a male is 5'9" right? So I wouldn't compare female to a male. But if I use this empirical rule, I can kind of figure out where most males' heights are. So if I go like this, 69 inches in the middle, add one deviation, add another deviation, subtract one deviation, subtract one deviation, 63. So I've been told I was short my entire life. And if I use statistics, I'm 5'5", 65 inches. Anything in that interval is considered normal height, right? So a male that's 5'3" to 6'3", that's normal height. Right, so I have average height. I'm actually close to the average female height. So I drew the curve that's spread out. Female height has less spread, so the normal curve is a little scrunched together a little bit more. So closer together, 66 in the middle, 5'6". Actually, that's a little bit of overestimate. I think it's actually 65. I got overestimated there. 65, subtract 2.5 inches, 62.5, 60. So most females, 95% of females are between 60 and 70 inches, which is 5 feet tall or 5 feet 10. Okay. Are there females above 5'10"? Yes. Okay. Are there males above 6'3"? Yes. It's just we think that there's a lot more males above that height because we have something called the NBA, and pretty much anyone that's tall plays in the NBA, right? So we think that there's a lot more people in that group, but there's not. Okay, because we just don't see them on TV. Same thing below 5'3". Okay, there's males there below 5'3". Same thing for females. It doesn't cover every person. It's just a percentage about. It's an estimate. It's an approximation of different groups. Okay, so I could use this for different topics. For example, if you have two different classes, you have statistics, you have science. We can compare two groups. For example, in statistics, you take a quiz and you get an 85% on your statistics quiz. And the standard deviation is, so this is going to be the average. I'm not going to use a percentage. I'm just going to call it 85. So in statistics, the average grade is 85. Standard deviation, let me use S for sample data. S is 10. So that's your statistics class. Unless, what would I say, science? So it'd be, it's called biology. Biology, the average grade is an 88. Standard deviation is 15. Now let's consider some scores. So you take a statistics quiz and you get an 86 on a statistics quiz, and you get an 87 on a biology quiz. So then you go home and you tell your partner or whoever you're with, I got an 87 on my biology and I got an 86 on my statistics. They go, oh, you're a lot smarter in biology, right? Oh, you're better in biology. That's your good class. Well, we got to compare it to the average score. Okay, that's why we use, and the standard deviation measures the spread, how spread out our data is. So if the average score is 88 and you scored 87, you're below average in biology. The average score in statistics is 85 and you scored 86. We got to compare those two things. So that's another use of standard deviation. It measures the spread. Okay. That makes sense? So I could use standard deviation to measure these things using the empirical rule. We're gonna get into like a lot of detail about using mean and standard deviation as measures of center, using the empirical rule, using a percentile, and comparing different values. Okay. So again, we just learned how to calculate the standard deviation, but I think it's good to know how to apply it. There's another rule. There's two more rules for measurements of variation. There's Chev's rule, and there's the coefficient of variation, which I don't feel like are too important because they're just mentioned once again, like the mode. And so Chev's rule, some person named Chev said, you know what, that 95%, that 68, 95, 99.7, I don't think that applies to the entire population. So different idea. Okay. Everybody can have different ideas about different things and different definitions. 68, 95. Oh, that doesn't work. That's not a very good measurement. So Chev uses 75%, 88.9%, and 92% for 1 deviation, 2 deviations, 3 deviations. Okay, and that's on page 89, Chev's rule. Not too important to apply his rule. I don't know. That was like, I don't know what year that came in, 1821 through 1894. So the mid 1800s came up with a new rule and said, hey, I want this new rule. And didn't pan out very well. Most statisticians are using normal distribution. The coefficient of variation, again, we can compare two groups and say which data set has more variation. Is there more variation in this data set over that data set? Like I had nurses and engineers up here, right? So we have which one has more variation. Well, I could just look at standard deviation, but the coefficient of variation actually will calculate which data set has more variation. So in order to do that, you take the mean and the standard deviation and divide them. That's it. Page 92. I think I assigned one question about the coefficient of variation, all right? You just take the standard deviation and the mean and just divide those two values. Pretty straightforward. Okay, it's like a fraction, right? And there's an example there. Coefficient of variation of height and weight. Okay, so they have height and weight. Height has a variation of 4.5. Weight has a variation of 9.4. So there's more variation in weights than there is in heights. Cool. That covers pretty much everything in 2.4. That is a need to know, covering the need to knows. Page 93, 2 through 28, even. And then I assigned 33 through 38 because they're all 33 through 38 talk about the empirical rule. Actually, I'm going to change that. Let's just do 33 and 34. I'm going to get rid of that. Let's do 33 and 34. I'm going to get rid of all the Chev's ones. And then 43 and 40. Let me check those real quick. Comparing two data sets, Dallas and New York City. I like that one. 43 and 53. Okay. Acceptable. I'll change it on the thing.